While browsing around on eBay for some lights, I came across this sign. It was actually a seller who was selling sort of small high bay light type things. And one of their listings was this open sign, but it was also listed next to emergency exit signs. And if you look at the listing, it says Bayard LED maintained, non-maintained emergency light, open light. And why would you have an open light that's an emergency light? And I just guessed maybe they'd copied and pasted from this listing. And this seller was David's Group in the UK. I also noticed that one of their partner companies was Ben's Group. It seems to be a few different sellers going under the same sort of banner. However, this sign, I decided, well, let's power it up. It takes about 35 milliamps. Power factor is about 0.5, suggesting maybe a capacitive dropper. Power dissipation is only 1 watt, and if I turn the light off, it's okay. It's clearly got 3 points of light shining down with a light background to make the light sort of come through the front. But here's the thing. When you disconnect it, and that's it disconnected now, it is actually an emergency light. This is the wire. I've just pulled it out completely. It's now standing on its own. It's an open sign you can't turn off, and that doesn't seem like a very good idea if you're operating a shop and you go to turn the open sign off at the end of the day and it just stays lit. So let's take a look at this. So let's lock the intensity now and we'll take a look inside it. So this is lit right now. I've checked the grounding, and there is earth continuity from the earth wire here onto these sort of metal hang bits, but not onto anything else. This top aluminium extrusion, yes, but none of the other ones because they're joined by plastic. So let's try and open this. I'm not sure it's batteries inside. The listing implied. Oh, I should also mention, it's got a couple of indicators in the end. It's got power, trouble, charge, and a test button. And when you press the test button, it does switch to battery. I was saying something there and I've just completely forgotten what it was. Well, that doesn't matter. Let's open this. I mean, it does say open after all. I think that's what it wants us to do. I'm wondering, there's a sticker at the side. Oh, right, okay. Yeah, oh, I've just snapped it completely. Okay. That's not coming out easily. Is that locked in somewhere, glued? I think this is going to break. Well, I think it's already broken. I think I've just used unreasonable force. I don't see anything specific holding it in. I can see LEDs glowing brightly inside. Green LEDs. I'd like to mention that if you used something like this, is this glass or plastic? Oh, this is actual glass. It's very scrunchy and... Ooh. That's glass. I wasn't expecting that. Screen printed glass with the sort of open sign in the back, and then that's just slightly diffused wide emitting LEDs at the top. I thought there were 4, but there's actually 1, 2, 3, 4, 5, 6. There's a little remote controller PCB. There is the capacitive dropper. There's the circuitry. Then there's a little inductor here. Oh, it's basically got what looks like an emergency, a garden sort of solar light type thing to step up from the NiCad. So it is a NiCad battery. And let's get this all out. So I'll just drag this cable through. I suppose this could be used for other applications. Oh, that's on a little sort of carrier that rides up and down. It's quite interesting. I'm guessing the other bit's on a carrier as well. Will it slide out? I'm not so sure. Oh, it's these screws are holding it in position. Oh, that's what I was going to say, yeah. I wouldn't recommend, if you were getting emergency lights, I wouldn't recommend getting cheapy things like this off eBay, because if you have a venue and you have a fire in it, and it turns out that you'd got the cheapest, shittiest emergency lights off eBay that you could find, that is really close to the earth terminal. That's quite odd. Yeah, that could lead to serious repercussions. even if the lights had performed properly, they might sort of get a bit ratty about the fact that you cheaped out and not had the proper thing, the proper certified ones. I'm saying that because they do this in the sort of one with that does actually say emergency exit. So are these glued in? It doesn't seem to be coming out too easily. Oh, it's got a label across it. It is actually held together by sticky tape. Yeah, that's better. But these ones are not held together by sticky tape. Well, I'd say that's open now. Is that glued in some way? Nope, it just seems to be a friction fit. So this is a module. Let's squeeze those in with a pair of long nose pliers. This is where I don't find the long nose pliers that I'm looking for. These cheapy ones will do. Oh, these are little press-on pillars, but I don't think they're going to liberate too easily. No, that's very much a press it on really hard and they're not going to come back off again. Why are there... Oh, you know what? It's got that one that says trouble, but I don't actually see an LED under it. It's actually only got 2 wires coming down to this for power and charge, which are in parallel, I'd guess. No, they're in series. So power and charge will both light together. And when you press the button, it just shorts those 2 wires out. This isn't coming apart that easy, is it? Maybe I should have paused. Too late now. Well, I could always edit out afterwards, but having said that, when I edit things out, people seem to actually express a preference to actually seeing stuff that is left in. I think I'm just going to cheat here. I'm going to cut that off. There we go, that worked. Yeah, these little plastic pins that they've pushed on are very sort of splayed out and chewy. I think I'm going to have to cut them all off. Let's cut them all off. There we go. Nice housing, nice frame. So here's the circuit board with the mains coming in at the end, very close to the earth connection that had the sort of lug sticking down, like really sticking down where that circuit board was. Right, I think I'm going to investigate this and I shall be back in a moment. The deed has been done, the circuit has been reverse engineered, and like all good cheap stuff, it uses lots of clever tricks to achieve good results. Well, all the results that it needs to present itself as an emergency light. Perhaps not a fully compliant emergency light, but an emergency light nonetheless. The main circuit is actually fairly complicated, but it breaks down into sections. You've got the test section, you've got the battery charging section, you've got the latch section for switching it on when the power fails, and you've got the inverter section that drives the LEDs. So let's initially take a look at the power section, because it's quite nice that on the circuit board, you've got the power sections here, the latch sections here, the LED driver, the inverter sections here, and the charger sections here with the nickel-cadmium cell. Nickel-cadmium because they're more resilient to continuous trickle charging, and it is being continuously trickle charged but at very low current as it transpires. This isn't going to recover in one day. This is going to take up to 3 days to fully charge, but that's okay. It certainly means that the cell's not going to get too stressed that way. So let's take a look at the power supply circuitry first, which is a simple capacitive dropper because it's the cheapest and simplest way to do it. So the capacitive dropper is based around this big red capacitor here, and this bridge rectifier based on 4 discrete diodes here. And here's the first interesting trick they've used. So we've got the 470 nanofarad 400 volt dropper capacitor with its 680k discharge resistor across it, the 4 diodes forming a bridge, a smoothing electrolytic, and then the voltage is capped by the LEDs themselves. If the power is on, the LEDs have to be on. They're part of the voltage capping circuitry. And the LEDs are fed via a diode and then the 6 LEDs in series. And the 6 LEDs in series, they're being run about 20 milliamps. So their voltage will probably be about 3 volts across each one. The combined voltage will be about 18 volts plus the diode, let's say 19 volts for the power rail. And the reason they're fed by the diode is because they can be fed from either the capacitive dropper or the inverter circuit over here via this high-speed diode. The test module, the little circuit board for testing it that has the power indicator, the charge indicator and the test button, it's quite amusing in the sense that the LEDs are both in series across the power rails with a 10k resistor, so as long as the power's on, they'll both light. The charge indicator doesn't really indicate that an actual charge is going into the cell. If that cell was chopped out, it would still light the charge indicator, so that's a bit naughty. The test button is hilarious because all it does is it shorts out the whole power rail. It just shunts the output of the capacitive dropper, and because the capacitive dropper will effectively just limit the current under those circumstances, it works. It means that that's going to see quite a spike of current when you press it, but it will effectively, very effectively emulate a power failure by shorting everything out. Now this is where it might be beneficial to zoom in a bit, because let's explore the circuitry itself. So we've got the test circuit out the way at the end, which is the 2 LEDs in series with the resistor and the button to short out the rails. Let's nudge this in just a little bit, not too much. And we've got the battery charging circuit, which is super simple. I mean, it couldn't be any simpler. With nickel-cadmium cells, you can just keep charging them, as with nickel metal hydride. You can keep trickle charging them because when they get to the end of their charge and the electrolyte starts gassing off in the electrodes, it gets chemically converted internally back into the electrolyte, and they get slightly warm. This one isn't going to get warm because the charging current is so minute. But it doesn't harm them, so they can be left trickle charging continually, and the lower the charging current, the better. So in this case, all they've got is a diode, a 1K3 resistor and the cell. That is the whole charging circuit. It's just 3 components, the diode, resistor and the cell. And I would say that the charging current is going to be just marginally over 10 milliamps with that arrangement. And this quarter-watt resistor is actually operating around about 200 milliwatts. Initially I thought it was going to be quite pushed because it was the only thing limiting the current, but the current is effectively so low they've just balanced it off to match the resistor. So that's the test circuit, that's the battery charging circuit. Let's look at the inverter. The inverter here is based on 2 transistors, and it's very similar to the little circuits that used to be used in flashlights, the first LED flashlights that ran an LED or more LEDs from a single cell. And it's pretty much what it's doing here. It's very simple. It's got an NPN transistor, PNP transistor, a bias resistor to just nudge that PNP transistor on, and then a feedback capacitor and the inductor itself, quite a chunky inductor. I wonder what current is flowing through those LEDs when it's actually running under that mode. I could test that. I can test that. I will test that. So when this is enabled by being switched by this transistor, which forms part of the latch that turns it on, that effectively just oscillates and it generates it pulls this inductor down to ground and then releases it, and it is, as someone recently described it, a bit like an electronic ram pump, a water ram pump. It's kind of like that. But the collapsing field there, the transient that's created when you switch this inductor down to the negative rail, and then the transistor turns off, then goes through this high-speed diode, and then it lights the LEDs. So the LEDs there can be lit either when the power's on via this diode from the main rail, or via this diode from the inverter. So there's two ways to light them. The latch circuit is clever and also it's a bit of a brain melter, because it's basically two transistors, NPN and PNP, but they've actually got feedback to each other's bases so that they'll latch in one of two states. And as well as latching, this one here, the PNP, is also switching the full load of the inverter circuit. It's all very cleverly done. So when you've got power there, the best way to describe the latch circuit is that, as in this case, this battery has got a charge in it, but the LEDs aren't lit because it's in an off state. If the power is then applied, now this is how it would normally be shipped and and installed. You'd normally have the battery connected at all times, but although there's no power there, it won't be trying to light the LEDs because the latch circuit will be holding it off. When you power it up, the circuit up, it will then set this latch into the opposite state by biasing these transistors. And the diode is there to provide a strong pull-up to this transistor to make sure it absolutely stays off when the power is there. And when the power is then turned off, the current will flow from the battery side to... What's the best way to describe this? What is the best way to describe this? As the voltage drops, this transistor effectively turns on and pulls this transistor, its base, down via this fairly low value 470 ohm resistor, and that turns that on quite hard. But then that transistor then, as well as turning this circuit on, then pulls this resistor here up to the positive rail and then provides extra latching current to this transistor. So it's a kind of like each one depends on the other. It's quite hard to visualize. It's quite hard to describe it, but it is a sort of double latch. It can latch in the on or off state. Can I prove that? If I was to shunt this transistor here, that should turn on. So that's this transistor here. And if I bridge the two outer connections, collector and emitter, with a pair of snips maybe, that should make the LEDs turn on. Let's see if I can not short something out here that's not... There we go. It's turned the LEDs on. At this point I can also get the meter and check the current. I'm just going to grab a meter. I'm going to put this around about 200 milliamps DC. That's AC. That's not going to help much. 20 milliamps. 200 milliamps. And I'm going to actually just shunt one of the LEDs. And we'll see what sort of current is flowing through that circuit. It will give a rough indication. 9 milliamps. That's not bad. That means that when the... I'll just switch these leads back. Never leave your meter set to amps because it's a dead short between the leads if you do that. That means that from the on state of 20 milliamps, it drops down to 10 milliamps in standby mode. And that should run then. 10 milliamps minus the drop. Oh, keep in mind that's them in series. So that's 10 milliamps at about the 18 volts. Yeah, it's going to be. This is going to last a modest length of time. That's going to last at least the 3 hours, I should think, that's required for these things. Now, can I turn this off? How would I turn this off again? If I shorted the base to the emitter, that should then turn that transistor off, and it should then remove the latch up to that. So that's the base and the emitter. Would there be this transistor, screwdriver? If I short the two right-hand pins of that, yep, turns off. They've got a capacitor across them, so it will dim away gently as it's doing. Yeah, so that's an interesting circuit. It's very minimalist. It's kind of, if I suppose ultimately in countries that have lesser standards, it would do the job. Certainly for home use, it would do the job. I'm not so sure about the green. I'd maybe want to adapt it, put white LEDs in. That would be quite interesting. But technically speaking, you could put this into a channel just forego that. It'll operate fine without this. This is just basically just patched across the power rails. But you could theoretically put this into a little channel, keeping in mind that it is mains voltage, and put warm white or cold white LEDs in, make a sort of little emergency baton out of this. And of course we've got all the aluminium extrusions to play with for the signage itself and the aluminium backplate. So I get the feeling they were selling those off cheaper because, well, there's no logical reason you'd have an open sign that has emergency functionality. I think they've just kind of, I don't know why they've done that. It's a shop that remains open in power cuts. That's the only thing I can think of. But yeah, it's an interesting circuit. It was really fun to reverse engineer. I shall remove this and let you, if you want, you can just grab a frame of this image just to follow it through yourself. But yeah, it's very neat. It's quite an interesting little circuit. It was quite fun reverse engineering it. I've got one small detail to add. It's a modest detail. It's two components. There are two capacitors across the LEDs themselves. There are a 100 nanofarad and a, let's see, what is the value of that? 47 microfarad, 25 volts. So let's say 47 microfarad, 25 volt, and 100 nano, just this little ceramic capacitor across the LEDs. Not sure 100% why. I guess it's just down to prevent flicker. Well, you know, there wouldn't be flicker because there's that. I don't know why they add those capacitors there, unless it just makes this section of the circuitry more stable. The latch circuit is perplexing because initially in its off state with this transistor off, because it's being pulled to the negative rail by this 4K7 resistor, when you apply power, and keep in mind it's about 19 volts, not only will it bias this transistor on, but it will also a lot of current will flow through this 2K7 resistor, best part of like 5 to 10 milliamps, and through this diode, and that will effectively turn this transistor hard off. But when you turn the power off and the voltage starts to fall, first of all, the bias is going to be removed from that. So it's quite a delicate balance of these resistor values. The bias off is going to be taken from this transistor here, and before the voltage can go low enough for this transistor to lose its bias, this transistor will turn that transistor on, which will then turn that circuitry on, and then provide the feedback through that resistor to keep that transistor on. So it's all juggled with these resistor values. It all happens very quickly. It's like an instantaneous thing. When the power goes off, it's quite neat. It's a very simple arrangement, but clever.